Bob's doing homework.
I went outside and did homework on the wall.
And that is your first question.
Wow.
Yes!
I looked in the sky, but I did not see the moon.
It was there.
Sorry, it just somehow.
I guess the minute that I was outside. And
Nobody observes the blood.
Wait, what's the
Class, it's like,
Am I going
I don't
in?
know what I watched. It's only class they use 33 for.
Use your classes.
Eliezer?
No, wait, wait.
It's not that hard of a question.
I'm trying to cheat off a code.
I'm looking around.
Okay.
That isn't code E and a KLM.
Now, yes, there's no right answer or wrong answer here, but I was just a curious thing. Did you go out and observe it? I went out and observed it, mostly because my wife thought it would be cool.
Aww.
Yeah.
My girlfriend had never seen a lunar eclipse either, so
Really?
yeah. So I
See,
had to explain to her why it does.
yeah. Oh, I did that, believe me. I said, now, who can tell me where the sun is right now? I was very proud that both of my wife and my son were able to tell me. Caleb, where would the sun have been?
It
Since
would have been in the west, like behind, right?
yeah, you just point to the moon, exactly opposite, right? Because the Earth is between the two when you have the lunar eclipse.
They have a Snapchat story for it, so you can rewatch it.
Because lunar eclipses are so doggone exciting. Okay, question number 2. What is a supermoon?
Nothing special. Is there a wrong answer on this one?
Yes, there is a wrong answer. The wrong answer is the one nobody selected. The other two are correct. There's nothing really special about supermoon. I was like, everybody keeps talking about supermoon. Woo, woo, woo. You know, having an eclipse during a supermoon that happens once every generation or something. The last one was in 1982. Next one will be in 2000 again. You can tell I'm
2033.
yeah.
Supermoon, what is this when the moon is closest?
So yeah, I looked it up. It's a term some astrologer made up, you know. When the moon is, and it's a term that's used for when the moon is close to the Earth when you have a full moon. And so when the moon is closest to the Earth, we actually call it the well, in any orbit, it's the perigee. I don't know if there's a special term for closest to Earth. We have perihelion for when the Earth is closest to the Sun or a planet's closest to the Sun. Perigeo for the Earth. Very nice. So this here, closest to the Earth, is called perigee. So when the moon is at perigee, it's closest to the Earth, it's going to make a bigger angle. Remember that small angle formula. If you have it closer, you're dividing by a smaller number, so it makes a bigger angle. But of course, the moon's orbit is pretty close to circular, so the difference in the biggest angle it makes and the smallest angle it makes is really a small amount. So we tend to not get too excited about this, except for apparently if you're into astrology. So yeah, the article I read was, astronomers could care less about a supermoon, but other people are getting all excited, and who am I to tell you not to get excited? Now some things that are just kind of bookkeeping announcements. Announcement number 1, if you haven't figured it out, is there's not homework that's going to be due on Wednesday. The reason is fundamentally we did a bunch of reviewing and didn't have any new material to have homework on. I could have had homework on 2 units or something like that. Well, that wouldn't have been worth your time. So there's no homework that's due Wednesday. There will be homework, of course, due the week following, just like normal. The tests, they're all graded. when I came into class, she had gone upstairs to scan them so then she can upload them to me. Oh, she brought them while I wasn't here. Okay, well then they're right here. I'll hand them out now because people always get confused about how do I read my score? Thanks for pointing that out.
Yeah, is there a midterm?
This is one of the midterms. To me, midterm means an exam given in the midst of the term.
Yeah.
To other people, midterm means an exam given at the midway point. That's not the way I use the word. So this is a midterm. There will be 2 more. You can tell her handwriting is much better than mine.
Well, this isn't yours.
Should I look at it?
I'm nervous. I'm nervous.
Dude, I have a problem. Oh, I didn't need a bathroom.
Okay. Now, for how to read it, because people get confused, we try to make it as clear as possible. You will see things like at the top, it says the number of questions you got right. So let's say it says 42 correct. And then it says something like out of 50. That's the raw score on the Scantron, 42 out of 50, if those were your numbers. Your overall grade, of course, has the additional 8 points coming from the scientific method. So handwritten, you should have plus, like, let's say 6 out of 8 equals, in this case, it'd be 48 out of 58. And that is your grade. Now, I haven't even looked at how the grades break down. I haven't looked at which problems were missed and that kind of thing. So I'm going to look at those things. I might grade out something smaller than 58 depending on what I see when I look at those. Like if there's a question, when I look back, I'm like, oh, that was ambiguous. I didn't think that So I may go back and change it. You'll also notice there should be another thing that says, like, say, M3. That's a ranking between B1 for beginning understanding of the scientific method to, I think it's C4 for showing that you have completely mastered it. The M2 and M3, the M stands for mastery. They're terms that mean little to me overall.
So what do I plan?
Well, if it's not on the grade sheet, it will be on the back sheet. That means that you showed complete mastery of it.
B1 is I'm starting to get it?
B1 is you're starting to get it.
I'm starting to get it.
Okay, so that's how to read that part. Then underneath you have the key and your answers. What does it actually say? It says key, and then what does it say underneath that? Okay, answers. And it has 1, 2, 3, 4, 5, blah, blah, blah. And then it'll be like, they're all true and false for the first 5, so I'll just put A, B, B, A, B. So those are the correct answers that I put there in red, the A, B, B, A, B. Then in the line below, it'll be something like dash, dash, A, dash, A. The dash means you were right, so you answered whatever is above. If it has a letter, that means you were wrong, and that's what you answered instead of the correct answer.
Yeah.
Because a lot of times people come and say, but I answered A. Yes, but the correct answer was B. Right, so understanding how to read that helps people to avoid confusion. So, like I said, I don't know what the top score was. I don't know what the minimum score was. I don't know any of those things yet. But I will look them up over time. Sometime soon.
If there's a, like, no 100% that you're going to quote it.
Well, I will look at things like the questions that people missed the most. And if the questions people missed the most are ones they should have known, then no. But if the questions that people missed the most are ones that might have been ambiguous or, confusing in some way, then I will consider doing, lowering the amounts out of. So right? Because I have to do some analysis. I don't just blanket, sure, yeah, I'm going to do whatever it takes to make sure that the whole class gets A's or, I mean, I know that's a theory that people would like, but we want the grades to, as much as possible, be effective measurements of what you showed on the test. Okay, moving to new material, the Doppler effect. During the student's presentation, we had some discussion about the Doppler effect, the whole idea. The reason the Doppler effect occurs is because the waves are traveling through space. Now, sound waves and light waves actually have a different Doppler effect method. The reason for that is because light in vacuum travels at a constant rate. It's not reference to or relative to a reference frame. Sound in air travels with respect to the air. And so that's what makes the two different. So here we're just looking at light waves. If something is moving toward you, you have a light wave, something that's producing waves that have peaks. And there's a certain time between each peak. And there's a certain distance then that the wave travels from when you emit one peak to another. But if the source that's emitting the light is moving toward you, then the actual distance between the peaks is less than the distance that the light traveled in the time between emitting the peaks, because your source was chasing the light. So to try to illustrate that, you have, if the source was stationary, you would have at time 1, it emits a wave. And then if we wait to time 2, this first wave will be out here, and it will emit a new wave. And then time 3, you would have, see, I went out 1, 2, 3, 1, 2. You'd have the first one would be out here, the second one would be here, and the third one would be there. And they would all have an equal spacing that we call the wavelength. That's what happens with the stationary source. But if I have a moving source, start with the same initial source, so my top lines will stay the same positions, but then for the emission of the second one, it will have moved forward. So at the time that it emits the second one, my source might have moved forward to here, so the second one is emitted here. And so now the spacing between these is less than it was initially because the source moved forward in the time between one emission and the next. So the wavelength is shorter between them. And so that's illustrated in this picture. If it's coming toward you, the wavelength is shorter because the source is chasing the waves, catching up, kind of. If you're on the other side, the source is moving away and there's a bigger gap between the waves. So a bigger wavelength means a lower frequency. So you have this Doppler shift because of the moving source. And this here is our equation for the Doppler shift. That equation right there. This V we call the recessional velocity, or sometimes the radial velocity. Recessional velocity means the speed at which it's moving away from you. So the speed something's moving away divided by the speed of light is equal to delta. What does delta mean? Change. So the change in lambda, what does lambda mean? Wavelength. Change in wavelength divided by lambda sub 0, the initial wavelength. The change in wavelength means the wavelength you measure minus the wavelength in the laboratory. Z is a symbol we often use for the redshift. So you might see something, they say it has a Z of 0.17. That means the speed divided by the speed of light is 0.17. C is the speed of light, V is the recessional velocity. So you just have the wavelength shift is equal to that Doppler shift Z. Now why is this important? It's important because a researcher was looking at spectra, and the spectra looked kind of like the spectrum that you get from a hydrogen atom, but everything was shifted a little. And I'm pretty sure it was a she. She figured out, hey, if everything was Doppler shifted by the same percentage, it would be correct. And so then she said, okay, well, let's do that. Let's figure out how fast it's moving, blah, blah, blah. And that's the beginning of understanding, hey, things are moving away from us. They're not just stationary, staying the same distance away from us. Further observations showed that virtually everything is moving away from us. There are only a small number of things moving toward us in the entire universe. And so oftentimes people will say, well, if everything's moving away, that must mean we're the center. I had this conversation with somebody last week. That's an incorrect evaluation. If things are expanding, it doesn't matter where you are, it's going to look like everything's moving away from you. So everything's moving away from us, but if we were able to transport out to something very far away, from that reference point, everything would also look to be moving away. And we can measure that by using the Doppler effect. The Doppler effect is actually used for more than just, I guess I better talk about this. It's the next slide. It's used for more than just determining if things are moving away. We did talk about redshift and blue shift when Eliezer was talking about it. Redshift is a shift to longer wavelength. Actually, it says right here, longer wavelengths, and corresponds to the source moving away. So, what are most things doing? Are they red shifting or blue shifting?
Most of them are red shifting.
Most of them are red shifting because they're moving away from us. Blue shift would be if something's coming toward us. And these pictures here are showing, what kind of spectrum is this? It says, but
that's an emission spectrum.
It's an emission spectrum because you just see the lines. This one here is an absorption spectrum. And you might ask, why do we see emission spectrum and compare it to the absorption spectrum? Because in the laboratory, you saw I brought out my lamp, and we saw the emission spectrum from the gas in the lamp. That's the easiest thing to make and analyze. But the stars are giving off continuous radiation because they're hot. And then we see absorption spectra because of the gases in their atmosphere. So when you look at a star, you see the absorption spectrum. So that's why it's showing the two, because that's actually what we compare. Now remember, the lines are exactly the same in the emission spectrum and the absorption spectrum. So in theory, this line should have hit that one. And this line should have hit that one, and so on. That one wasn't a straight line. But in practice, they don't. The reason? This one here shifted a little bit. Now notice it says it's going 0.7% the speed of light here. What would the z value be if it's going at 0.7 the speed of light? Okay, 0.7 would be 0.007. So that's a pretty small shift. And so it's showing us the actual shift for something, and we can determine how fast it's moving based on that. And yes, this is on top of words. I was going to fix it. I had a student in my office and obviously forgot to. Other things we use the Doppler shift for. Rotation rate of objects such as the sun. The sun, of course, is out there, but the sun is rotating. And so we look over here and we'll see the spectrum shifted because it's moving towards us on that side. We look on, so what color should I have used instead of black on the side that's coming toward us?
You should have used blue.
Blue. So over here you have a blue shift because it's coming toward you. What do you have on the other side?
A red shift.
A red shift. And so looking at those shifts on either side, you can take the average between the two and say, okay, that's how much it's actually moving toward or away from us. And then take the difference from average to determine how fast it's moving at the equator. And so this can be used to determine the rotation rates of things like the star, or the sun and other stars, galaxies, planets, etc. So that's one thing, rotation rate. Another thing is motion of stars in a binary system. A binary system is a system that has two stars. An example of a binary system is Mizar. Who remembers where Mizar is located in the sky? Eleazar says Kendrick does. It's in Ursa Major. It's, well, no. If you look at the handle of the Big Dipper, you have Alcade, Mizar, and Alcor. A-M-A, Aliath, Megrez, Fecta or Fad, depending on where you look, Merak, and Dubi. And so that's Mizar right there. Yes?
This is off topic, but I was actually looking at one of those Sky View apps or whatever it was
Yes.
last night, and I looked at the Big Dipper, and it had a different name for Alcade.
Really?
It was a larger name. Have you heard of it?
I'm not familiar with an alternate name for it, but there are many stars that have multiple names. In fact, as I understand it, Alcor and Alcade are supposed to both be the same name. They're supposed to be the Arabic for the rider. Mizar is the horse and they're the rider. And different people disagreed on which star was riding which. So that's certainly, like I said, Fad and Fecta are used approximately equally as far as I can tell. So, yeah, you have multiple names sometimes. So it's not shocking. By the way, I was going to point that out. I'm not sure that I ever talked about apps for your smartphone, did I?
You mentioned it last.
Okay. Well, yeah. So if you have an Android phone, just get the Google Sky Map. It's free. It's really good. If you have an iPhone, I've got some different suggestions, that you can use. But they're really nice to go out and try to figure out where things are because it'll use your GPS and your compass and you just go like this and it shows you what's behind. Okay, so Mizar is an example of a double star. If you look at Mizar with the telescope, you actually see two stars. And by studying the spectra of the two, we can see that they're orbiting each other. And furthermore, if you look at the spectrum of just one of them, you see that the emission lines are in doublets, and those doublets will move like this, which indicates that you had two different stars that are going at different speeds. Sometimes one is coming faster toward you, and sometimes the other is coming faster toward you. And so what that indicates is each one of these, if we could resolve, we would see each one of these as two stars as well. So when you look at Mizar, you're actually seeing four stars there in Mizar. And Alcor is also a double. So between Mizar and Alcor, you have 6 stars, even though we only see 2 dots. Kind of cool, isn't it? Furthermore, this set of 2 and this set of 2 are orbiting each other, so you have something that's doing like this. It's pretty cool. So those are what binaries are. And the motion of the stars in the binary system, you have ones that we call spectroscopic binaries. We can only use this to determine that they're binaries. Okay, annual variations of the Doppler shift observed in the sun provide evidence for the motion of the Earth around the sun. Yeah, it's good to know, sometimes we're going toward the sun, sometimes we're going away. It's not a perfect circle. And then this one here, the very, very bad use. Police use this to take away your money. So we'll not spend time on that one. They've taken away my money a few times. Okay, another question for you. When observing a distant star, you notice that there is a series of absorption lines that match those of the hydrogen-Balmer series, but are all shifted a little shorter wavelength. What can you tell about the star? Yes, it's a clicker question. Things are getting better. I was worried for a while that I was just talking to myself.
He's not gonna get this one.
Tierney, do you have your clicker? Okay, it's channel 33.
Most of the classrooms, I don't know if you haven't been to that many, have like a little sticker or something in the corner of the room that says. One that actually was printed out, not just written.
I got it wrong now.
Okay, get your answer in there, Tierney. Oh no, Tierney's got a different clicker number. Let me write that down. So I can get him getting his scores. Okay, so the answers we got were 0, 11, 2, and 1. Now, that's a frustration answer. You should be able to tell something. Because you have a Doppler shift, the Doppler shift tells you about motion toward you or away from you. In this case, they're shifted to shorter wavelengths. What color has shorter wavelengths?
Blue.
Blue, okay? So it's a blue shift, and if it's a blue shift, then it must be moving which direction? Most people said toward, and I put the sun just so people would, we usually use the sun as our reference so we don't say, well, the earth was, yeah, some people get torn up about that. Okay, talking about telescopes. Oh, what was I going to say? There was one more thing I was going to say about, yes, one last thing. Remember when we went to the equation for the Doppler shift? It was the recessional velocity, the velocity of something moving away from you. Or sometimes they use radial because it can also be moving toward you if it's a blue shift. So the Doppler shift tells you how fast something is moving toward you or away from you. Award is not the combination of away and toward. It does not tell you how fast something is moving in a circle around you. In fact, if you take something like a whistle and you swing it around your head, you're not going to hear a Doppler shift because the sound is not getting closer or farther from you. It has to be coming toward you away to hear. So this doesn't tell you the velocity. It tells you the recessional velocity, how fast it's moving toward or away from you. So the tangential velocity, as we call it, the velocity that's staying the same distance but going around you in a circle, we have to find other ways of measuring that. Okay, now for this pretty picture. It's a cartoon. It's somewhere between a nova and a supernova. Probably a pretty good nova. I put this in here because, of course, he's looking through a telescope. And I've actually, in the past, taken the students out to University of Nebraska's research telescope in Meade. And you can actually look through the telescope, which is kind of a rarity because astronomers don't look through telescopes. No, it's not. I'm hoping it's clear tomorrow night. We'll go out and refresh ourselves on where stars are because it's been a while since we've done that. That's my hope for tomorrow. By the way, nova means simply new. And a supernova and a nova are two different types of things, but both of them you see something new that you didn't see before that lasts for a couple months maybe. Pretty good nova doesn't exist yet. That's the joke here. Okay, but we're going to talk about telescopes. And back in the old days, like, when Galileo was using a telescope, well, yeah, he was looking at it with his eye. But there are some reasons, some very good reasons we don't use our eyes. One of them is that our eyes aren't very sensitive. You have to have brighter light to see things with your eyes. Now, your eyes can adjust to become more sensitive if it's dark. So when we go out to observe the sky, we don't like to have somebody turn on their iPhone and make a bright light because then our eyes will become less sensitive when we're looking at the sky. and it takes a while to adjust. I read about some researchers who were doing some work in absolute black, and they would go into the room and sit there for an hour just eating donuts and kicking back, waiting for their eyes to adjust to be as sensitive as they could be for them to work in this absolute darkness. So our eyes aren't very sensitive to dim light. We don't see colors at all in dim light, like I said last time we were out there for lab.
Because rods. Because rods.
Right, because the rods are not color sensitive, only the cones are. Film is sensitive to about 10% of the light hitting it. And so for a long time, film was used by astronomers. They would take photographic plates, pictures of the sky with a telescope, and then they would examine those plates. And let's say you're looking for a comet. Comets would move, from today to a month from now. And so they would use a flip camera where they would have two pictures taken of the same part of the sky lined up very carefully. Then they'd flip back and forth between the two and look for anything that shifts when they shift from one picture to the other. To me, that would be incredibly frustrating. But that was how they did things, like look for comets or look for planets when they were looking for planets. It was with those flip cameras and film. Nowadays, we got these new highfalutin charged coupled devices, CCDs. I got a CCD right here. The camera there uses a CCD. I also have a front camera on this, uses a CCD. Those charged coupled devices are everywhere these days, and we take lots of pictures with them. One of the great things about the CCDs are they are much more efficient than film. They record about 75% of the light instead of about 10%. So to get the same amount of information, you would have to use film 7.5 times longer than you have to use the CCD. Furthermore, the CCDs allow you to do things like check how much light you've received. If it reaches a limit, we'll stop the exposure. If it hasn't, we'll keep the exposure going. Or we can do a whole bunch of exposures and on the computer immediately combine them to make one. So there's a lot more flexibility with using the CCDs. Now, we're not going to talk about the physics of the CCD, but it uses the fact that photons come in packets of energy, and when that packet of energy hits the surface, it will kick an electron off, and you just measure how many electrons got kicked off, essentially. It's obviously more complicated than that, but that's what we use these days for telescopes. So astronomers, you guys know Elena Cornwell?
Yes.
Okay. Her dad was a year ahead of me in high school, so I know him. And he, for a while, was working with the Keck telescopes in Hawaii. And they have people like him. Their job is to make sure the telescopes are operating. And then other people, the astronomers, control the telescopes, aim them where they want to aim them, take the pictures they want to take, and they can be doing this from the comfort of their home in any place on Earth. They don't have to go to Hawaii. Of course, they would like to, probably. But they don't have to go to Hawaii to do their research. They just control the telescope in Hawaii via the internet. So these days, being an astronomer doesn't require you to go anywhere special. You don't have to go to Hawaii or Arizona, the two most common places. You could just stay at home and gain access to a telescope. And the telescopes take the pictures, and then you do the analysis. It's actually pretty similar. You guys have probably heard about CERN basically in Geneva. And you have beam technicians who are running the beam, and they do these experiments. The experiments, many of them are like well-defined. Okay, so we're going to do all this, and we're going to make these measurements, and then everybody analyzes the data for the thing they're looking for. So like last year, some people from UNL were talking about, okay, so we have developed this analysis that we're going to do when they get the next batch of data. And so we're all ready. As soon as they get that data, then we'll do our analysis and try to find it. They don't have to go over to CERN to do it. Now, for some experiments, you do have to go over there, and it's an interesting world. So, astronomers look at this, and they don't just look at visible light. They look at lots of different wavelength ranges. This here is looking at what we call infrared, pretty sure, and this one's looking at ultraviolet. I'll just put UV for short. So they look at different spectra to see different types of things. This here, in case you're curious, is called the bipolar flow. You have jets that are shooting out in each direction, and these here are where the jets, essentially how far they've gone, where they're backing up. This here is a remnant of, it looks like a supernova. So the telescopes that they use, well, let's talk about this one first. This is something that's very cool. In 1054 AD, I put common era here, Chinese astronomers noticed a new star that only lasted for a few months and disappeared. We have the term nova to describe that. Nearly 700 years later, a British physician and amateur astronomer, that could be you someday, said, hey, I wonder what is located where the Chinese people saw stuff. He was probably thinking, we now have telescopes that can see things there. Actually, what year was that? 1731? Yeah. Had to have a telescope then. So we have telescopes, we can see things. So he looked there and he saw a fuzzy cloud where they had seen the new star. And that fuzzy cloud has been studied very, very carefully. We now call it the Crab Nebula. And based on the observations, we understand that to be the result of a star exploding. And so now we can work back and say, okay, well, if that's a star that exploded, let's use something to measure how fast the material is moving away. What would you use to measure how fast the material is moving away? The Doppler shift. So they use the Doppler shift to figure out how fast this stuff is moving, then they extrapolate backwards. Say, okay, if it's been moving that speed for all time, when was it just a single point? And they calculate that time as a single point, and they get back to the time that the Chinese observed this guest star. And so then they can say, okay, this definitely has to be the remnant of a star that exploded that the Chinese astronomers observed. Just totally cool.
Why do some stars last really long and some stars last only like 1,000 years?
Well, all stars last more than 1,000 years, but they have variations in the length of their lifetime based on how much mass they have. And we will study the evolution of stars very carefully, but to put it in short terms, bigger stars burn their fuel much more quickly. They burn their fuel proportional to the, oh, now I have to think about this. Well, yeah, I think it's proportional to the mass cubed or something like that. So they burn their fuel very rapidly as mass increases. They burn a lot faster. So big stars, even though they have more mass, they burn it so much more rapidly they live short lives. Smaller stars burn it much more slowly, and thus they last a lot longer. These are just more pictures showing the Crab Nebula here in different wavelength ranges. Let's get to some modern telescopes. This here is, I'm pretty sure, the Keck telescope. Notice it's a twin telescope. Has two telescopes. What do you see for the telescope there? What did you say, Ken?
Is that the one in Arizona?
No, in Hawaii. What do you see?
It has a covering.
Okay, it has covering. That covering serves a couple purposes. One would keep things like direct sunlight from hitting it when you're not using it. Another one is for keeping the temperature constant. They keep those covered during the daytime usually, open them up at nighttime. This picture's probably taken at nighttime with a long enough exposure that it looks bright.
So it will affect, it will destroy, in the daytime it will destroy them?
Well, if things get hot, they expand. If things get cold, they contract. And so they want to keep these at a constant temperature. So they basically keep them the temperature that it will be at night, which if you're on the top of a mountain in Hawaii is cold. So it's cold inside those telescopes. They keep the temperature constant, and then they open it up at night to do the observing. But what I see when I look at this is that you have two mirrors there. So this kind of telescope we call a reflector because it's using reflection of light for the telescope. Now you see these little things that look kind of like a tripod out in front?
It's like receivers that like it's a convex here, right?
It's a concave mirror.
Or concave mirror, I mean, and then it reflects the light onto that centerpiece, which reflects the light back into the center of those mirrors, which have holes in them.
That's right.
And that's where you see.
That's the design of these. So they're actually pretty simple, pretty open. They're easy to see what's going on, easy to work with, easy to mount the mirrors. There are many, many good reasons to use reflectors. This telescope is, of course, a famous one in Arecibo, Puerto Rico, or however you pronounce that. I would ask anybody here speak Spanish? I know. That's why I was going to say I would ask him, but anyway, Puerto Rico, for those of us who don't speak Spanish. The Arecibo telescope is 305 meters across. How does that compare to, let's say, a football field? A lot of us are familiar with the football field. How big is a football field? Okay, a football field is about 100 yards, not counting the end zones. A yard is a little bit shorter than a meter. So not counting the end zones, this is about 3 football fields. It's actually bigger than 3 football fields, not counting the end zones. If you were to count the end zones, it's smaller than 3 football fields. But that gives you an idea for how big across it is. It's huge. It's huge for a couple reasons. Number one is this is measuring radio waves. The radio waves are very weak. So you have to have something that's collecting a lot of them to get a strong enough signal to really see anything. So that's number one, a big area to collect a lot of the radio waves. Number two is radio waves are very long wavelength. And the resolution, that is the smallest detail you can see, is proportional to the wavelength. So you take these radio waves, one of the things they study with this is the 21 centimeter radiation that comes from electrons in a hydrogen atom flipping their direction of spin. So that 21 centimeter radiation, 21 centimeters, that's like what? Something about this long. Compare that to visible light, which is about 1/2 millionth of a meter. The resolution that you get with that radio wave is very bad compared to what you get with regular light, right? Like on the factor of 1,000,000 times worse resolution, which means the things you can see with this, if it was the same size as a normal telescope, would be 1,000,000 times larger for the smallest detail you can see. Well, that's kind of useless. And so they make it bigger because when you make it bigger, you can get better resolution. So they have to make it big, and we'll learn a little more about how that works. So this is a famous telescope. If you've ever seen like the movie GoldenEye, in the movie GoldenEye, this is the secret location that's filled with water, and then they drain it. And it's absolutely hilarious because when I was watching this in the theater the first time, I'm watching it drain and the walls are instantly dry after the water drains. Well, that's not the way it works. And then it gets to the bottom and the water jumps up and then goes down the drain. Now, of course, they weren't doing it with this telescope. They were doing it with a model. But pretty clearly what they did is they filmed it filling from the drain and then just played it in reverse. But, of course, things don't work the same forward and backward. Okay, moving on from the Arecibo telescope. Here are 2 versions of telescopes, a smaller one and a bigger one. The bigger one collects more light. Pretty obvious. Astronomers will call a telescope a light bucket. A big light bucket collects a lot of light. Like a big bucket would collect a lot of rain if it was raining. A small bucket would collect less. And so the collecting area, the area of your opening for light that's collected, is very important for a telescope because if you're collecting more light, you can see fainter things. So they talk about the collecting area or the collecting power, and that's going to be pi over 4 times the diameter squared. So if you make a telescope with twice the diameter, it'll collect 4 times the amount of light, which means you'll be able to see things 1/4 the brightness. For that reason alone, if you decide, I'm going to go buy myself a telescope so I can observe the sky, you want to spend your money to get the biggest diameter telescope you can afford. Because the bigger diameter is going to allow you to see fainter things. You can always, well, we'll learn in, actually not today, but the next class period, we'll learn that you can always just change your lenses to change the magnification. That's not a big deal. So don't worry about what's the magnification. Worry about how big it is. Now, it is also important, you do want to make sure it has quality construction and optics. You don't want to have, plastic lenses that were just drop fours. You want precision ground lenses. But assuming that you have quality optics, bigger is better. It also has, like I said, better resolution when it's bigger, so you can see better detail. Now, one of the things that scientists use that's kind of funny, well, it's kind of funny the way I used it, they'll use light filters. Filters that will filter out certain colors. Why would they do that? So you can see different kinds of details. So you can see there on the top left hand a spectrum. The U is ultraviolet, B is blue, V is green, R red, I infrared. Different filters that you can use that will allow light just in the region shown to come through so that you can see detail from that spectrum.
Why is green V? Why not G for gamma?
Verde.
Yeah, I'll go with that. That's a good answer, Verde. I don't know, but that's a good answer.
V for visible? I mean,
It is in the middle of the visible spectrum. I don't know. The way I used this was very bad. Back at PUC, we would open up the telescope on Friday night so the community and students could come up and view the sky every week. And so one night, for the fun of it, I put a red filter in and then I looked at Mars. And people were all, wow, I didn't realize it was so red. Yeah, that was bad. Yeah. Honesty and integrity. If you don't have those, what do you have? What were you going to say, Eliezer?
Did anybody ever catch on to what?
Oh, I told them. I can't let people go home and say, wow, Mars is really red. I didn't realize it. Mars is red. Why is Mars red?
Because it's oxidized.
Because it's rusted. There's supposed to be some big announcement from NASA about Mars today. I haven't been able to look at the computer today, so I don't know if they made it yet or not. Everybody's speculating about what this great announcement is, so keep your ears tuned to NASA. Okay, refraction. Refraction is the bending of light when it goes from one speed to another speed. Now you might say, wait a minute, we thought light had a speed that was constant. Light in vacuum has a constant speed. What's the announcement?
Liquid water exists on Mars, boosting hopes for life there.
I will wax eloquent as Dan Quayle. If we can find water on Mars, then there must be oxygen. If there's oxygen, we can breathe. He was our vice president. Doesn't that make you proud, the politicians we elect?
Who was?
Dan Quayle.
Quite.
Okay, thank you for looking that up. No, that was, of course, one of the most expected speculations because they've been looking so hard for water on Mars. Ever since Dan Quayle made that statement, that was justifying the money that we are spending to now be studying. Okay. It takes a while from start of the project to fruition. So light in vacuum always has the same speed, what we call the speed of light in vacuum, or the letter C. But when light goes through something that's not vacuum, it always goes slower. Basically, the light bounces off of things, gets absorbed, re-emitted. So it has to go at a slower speed when it goes through anything. So for instance, light going through air is a little bit slower than light going through vacuum. Light going through water is about 3/4 the speed of light going through vacuum. Light going through diamond is less than half the speed of light going through vacuum.
Whoa, really?
Yes, that's a big part of, actually, it's the primary reason that diamond looks pretty, because light goes so slowly through it. And because light goes so slowly through it, when the light goes from air into the diamond, it bends quite a bit. And then they make the backs of the diamonds. The diamonds are cut, so the back is something like this. You have the front like that. So the light that comes in, got to change color so we don't get confused. The light that comes in gets bent down like this and goes, and it comes out, and it can only get out at very specific points because of the way it's cut and because of how much the light bends when it goes in and out. If you had something that had a higher speed, you couldn't get as much of it. The light's focused and only comes out at these angles. Yes?
I thought that the speed of light was constant, though. So it's
In vacuum,
only in vacuum?
yes. In other materials, it slows down, and that's why we have this refraction. This little picture here is kind of a good explanation for it. Imagine you and a friend are walking down the beach at Huntington Beach, and then one of them strays onto the sand. What's going to happen to their speed when they get onto the sand? They're going to slow down because you got to kind of go through the sand a little bit. And so you're holding hands with that person. They slow down. You're going to swing around, and the two of you are going to now head into the sand at an angle instead of going straight down the sidewalk. You bent when you went in the sand because of the change in speed. And that's exactly what light does. And that's what the word refraction is talking about. It's that light bending as it goes from one material into another. And I will stop with this picture. This picture just shows a pencil. It took me a while, but I remember the name of that device. You laugh. It's not funny. Here's a straight line down the edge of the pencil to make it clear that, yes, there was a bend in what you see. Why do you see that? Not because the pencil bent, but because of the bending of the light going from water to air. Okay, I'll see you for lab tomorrow. Yes? Yes, absolutely. And did I get everyone their tests? Must have. There's nothing in here.
I'll be there.